Alright, let's start simple. You're on a road trip. You've got your phone on the dash, GPS running, and the odometer ticking up. After 2 hours you've covered about 120 kilometers. So your average speed was 60 kilometers per hour. Easy, but here's the thing. You weren't going 60 the whole time. Sometimes you were doing 100 on the highway. Sometimes you were stopped at a red light doing 0. Sometimes you were crawling through a school zone. So what was your speed at, say, exactly 1 hour and 43 minutes into the trip? Not your average speed. Your actual speed. Right at that moment. That's the question calculus was invented to answer. Here's how it works. Imagine plotting your position on a graph. Time goes along the bottom, distance up the side. The curve bends and twists depending on how you drove. When you're going fast, the curve is steep. When you slow down, it flattens out. Now zoom into any single point on that curve. Draw a line that just barely touches it, a tangent line. The slope of that line is your instantaneous speed. That's it. That's the derivative. Formally, we write it as ds over dt. The rate of change of position with respect to time. And that is exactly what your speedometer is calculating. Every single moment you're driving, your speedometer is a derivative. The odometer is the integral. And every car on every road is running on calculus. Picture a water tank. Big one, like you'd find on a farm or on the roof of a building. There's a pipe at the top. Water flows in. But the flow rate isn't constant. Sometimes the pressure is high and it comes rushing in, sometimes it slows to a trickle. Now here's the question. After 6 minutes, how much water is in the tank? If the flow rate were constant, this would be trivial. Rate times time equals volume. Done, but the rate is changing. Every second it's different. So what do? Here's the insight. Break those 6 minutes into tiny little slices. Say, 1 second each. During each second, the flow rate is roughly constant. So for each slice, you can calculate a small chunk of volume, rate times that tiny time interval, then you add all the chunks up. As you make the slices thinner and thinner, 1/10 of a second, 100th, 1,000th, the approximation gets better and better. In the limit, it becomes exact. That limiting sum is called a definite integral, and here's the beautiful part. On the graph of flow rate over time, each little chunk is a thin rectangle, its height is the rate, its width is the tiny time slice. Adding them all up means adding the areas of all those rectangles. Which means the total volume of water equals the area under the flow rate curve, area under the curve. That's what an integral is. Turn on the news during any outbreak and you'll see it immediately. The curve. That bell-shaped graph of daily new cases climbing, peaking, then falling. Everyone's watching it. Governments, hospitals, the public. But most people don't know how to read it. Not really. Here's what calculus tells you. The height of the curve on any given day is the number of new cases. But what you actually care about, what determines whether hospitals get overwhelmed, is whether that number is going up or going down. That's the derivative of the curve. When the derivative is positive, cases are rising. When it hits 0, that's the peak. That's the moment the outbreak stops growing. From there, the derivative goes negative, and the curve comes down. But there's an even more subtle signal. The second derivative. The rate of change of the rate of change. When the second derivative goes negative, the curve is starting to bend over, even if cases are still rising. That's the inflection point. The spread is slowing. It doesn't look like good news on the raw graph, because cases are still going up. You pour yourself a coffee. It comes out of the machine at around 90 degrees. You like it at about 60. So you set it on the desk and wait. Here's what happens physically. The coffee loses heat to the surrounding air. The hotter the coffee relative to the room, the faster it loses heat. As it cools down and the gap narrows, the cooling slows. Isaac Newton described this in the 17th century. The rate of cooling is proportional to the temperature difference between the object and its surroundings. Simple statement. Profound consequences. Written as a differential equation, it looks like this: dt over dt equals negative k times the quantity T minus T room. The rate of change of temperature equals a constant times how far you are from room temperature. Solve that equation, which means finding a function whose derivative matches this rule, and you get an exponential. Temperature decays smoothly toward room temperature, getting closer and closer but technically never quite reaching it. Now here's why this matters beyond coffee. The exact same equation describes how a drug concentration falls in your bloodstream after a dose. How a radioactive element decays over time. How a battery loses charge. How a charged capacitor in a circuit discharges. One differential equation. Dozens of physical systems. That's the power of mathematical abstraction. Look at any stone arch bridge, any modern suspension bridge, any Roman aqueduct. There's almost always a curve involved, specifically, often a parabola or a catenary. That choice isn't accidental. It comes directly from the physics of how forces distribute through a structure. In a parabolic arch, the compressive forces flow evenly through the curve and down into the supports. No bending, no tension, just pure compression, which is what stone and concrete handle best. This is why the Romans built arches 2,000 years ago that are still standing. But the engineer needs numbers. How much material is in the arch? What's the cross-sectional area? How much load can it carry before it fails? To find the area enclosed by the arch, you integrate. You take the height function of the arch, in this case a downward opening parabola, and integrate it from one end to the other. The result is the exact cross-sectional area. From that area, you can calculate weight, calculate compressive strength, calculate safety margins. Every structural element in every building, every bridge, every dam, was analyzed using integrals. The elegant curves you see in architecture aren't just beautiful, they're the visual signature of optimized mathematics. 3, 2, 1. The engines ignite, and for the next few minutes, something remarkable happens. A controlled explosion pushes hundreds of tons of metal upward against gravity at a rate precise enough to hit a target 300 kilometers up, moving at 28,000 kilometers per hour. How do you calculate that? Thrust isn't constant. The engines burn hard at launch, the profile changes as fuel is consumed, staging events alter the dynamics completely. So you can't just multiply force times time. You integrate the thrust curve. The total impulse, the total push delivered over the burn, is the area under the force versus time graph. That's one integral. From the impulse and the changing mass of the rocket as fuel burns, you get velocity. That's a second integral. Velocity is the integral of acceleration over time. From velocity, you get position. Height above Earth at every moment. That's a third integral. Markets are noisy. Open up any stock chart and you see jagged lines moving up and down, often apparently at random. How do traders make sense of it? One of the most fundamental tools is the derivative, not as a formula, but as a concept. The rate of change of price. When the price is rising quickly, the derivative is large and positive. Momentum is building. When it slows down and the derivative approaches zero, the trend may be running out of steam. When it crosses zero and goes negative, the price is falling. Algorithmic traders use derivatives of price curves, and derivatives of derivatives, to identify entry and exit points. Moving averages smooth out the noise by averaging prices over a window of time. The derivative of the moving average shows you the underlying trend direction. More sophisticated strategies use the second derivative. Is the momentum itself accelerating or decelerating? Is this rally picking up speed, or is it starting to fade? And on the integration side, the area under a supply and demand curve gives you something called consumer and producer surplus, the total value created by a market transaction. This is the foundation of economic welfare analysis. Wall Street runs on mathematics. And a significant fraction of that mathematics is calculus. You've got solar panels on your roof. The salesperson told you they produce 5 kilowatts at peak output. Great. But that doesn't mean you generate 5 kilowatts all day. Before sunrise, you generate nothing. As the sun rises, output climbs. It peaks around noon when the sun is highest in the sky and the panels are getting maximum irradiance. Then it drops off through the afternoon and hits zero again at sunset. So how much energy do you actually generate in a day? Power varies continuously. And energy is power accumulated over time. So to find total daily energy, you integrate the power curve over the daylight hours. The shape of that curve depends on your location, the time of year, cloud cover, the angle of your panels. But the method is always the same: integrate power over time to get energy. Utility companies do this calculation for every solar installation on the grid. They have to predict how much power will be available at every hour of the day, for every season of the year, to balance supply against demand. Grid-scale renewable energy management is, at its core, a massive integration. The moment you jump from the plane, two forces are acting on you. Gravity pulling you down. Air resistance pushing you up. Right at the start, your speed is nearly zero. Air resistance is negligible. You accelerate fast, at close to 9.8 meters per second squared. Free fall. But as you speed up, the drag force increases. It grows with the square of your velocity. So your acceleration starts to decrease. There's a speed at which the drag force exactly equals gravity. At that point your acceleration is zero, you've stopped speeding up. You've reached terminal velocity. For a typical skydiver in a spread position, that's about 55 meters per second. Around 200 kilometers per hour. The whole process is described by one differential equation. Mass times dv over dt equals mg minus bv squared. The left side is inertia. The right side is the net force. Solve it, and you get a velocity curve that rises quickly at first, then gradually flattens out at terminal velocity. You preheat the oven to 180 degrees and put the cake in. Here's what happens inside. The oven heats the outer surface of the cake almost immediately. But the center? That takes time. Heat has to conduct inward, from the hot surface, through the batter, toward the middle. At any given moment, if you could see a cross-section of the cake and measure temperature at every point, you'd see a gradient. Hot on the outside, cooler in the center, with a smooth curve in between. As time passes, the gradient flattens. The center heats up, the outside stabilizes, and eventually, if you leave it long enough, the temperature becomes roughly uniform throughout. This process is governed by the heat equation. It says that the rate of change of temperature over. Stand at the edge of the ocean and watch the waves roll in. They look simple. But what you're seeing is one of the most mathematically rich phenomena in nature. A wave is a disturbance that moves through a medium, in this case, water. The surface rises and falls in a repeating pattern. That pattern has a wavelength, the distance from one crest to the next. It has a frequency, how many crests pass per second. And it has a speed, how fast the pattern moves toward shore. The relationship between these quantities isn't arbitrary. Wave speed equals wavelength times frequency. In deep water, longer waves move faster.